Morning, everyone. So thanks for being here. I hope you enjoy your day. Not quite sure why I'm here. Somehow I'm supposed to give you some guidance and motivation for how to do research and how to make some career choices, I guess. So I have no training in those issues, no background, and very little knowledge. So all I can tell you is something about my own research interests, my own research program, and then I'll try and distill a little bit from that some ideas, which certainly have been highly beneficial to me about how you choose and how you carry out a specific research program. Okay, so I'm interested in quantum mechanics. So here's the traditional view of quantum mechanics. There's Schrödinger and Heisenberg. They both independently discovered quantum mechanics in the summer and fall of 1925. And the simplest way we understand it now is that everything, all objects in nature, are actually neither particles nor waves, but their dynamics is controlled by the Schrödinger equation or the Dirac equation. And so we describe every object in nature by this quantum mechanical wave function. So for example, an electron is not a little charged object. It's some kind of a quantum mechanical wave. And the solution to the Schrödinger equation is a complex field. So everything in nature is actually a complex number, which is a terrifying fact, which people are inclined to forget because none of us has ever perceived anything which is a complex number. You can't pay your bills with a complex dollar, and you can't drive a complex kilometer, and you can't age a complex year. But nevertheless, according to Schrödinger, everything in nature is a complex number. So Max Born, who didn't get a lot of credit for it at the time, though, tried to undo that problem by saying that things which can be observed are real numbers. They're this complex number squared. So that when you have a beam of electrons, the electrons are wave-like. They interfere with each other. Each electron is a well-defined particle. The interference produces a wave-like probability. Now, we all learn about this, and then we are inclined to forget about it. We rarely, if ever, observe anything in our own lives which has these properties. And we're taught, I guess, in high school and college to imagine that quantum mechanics is this deeply fundamental but hidden theory of nature that we never get any direct access to. And I strongly disagree with that, and my own research interests are not in these individual quantum mechanical objects, but in macroscopic quantum mechanics. And I believe that macroscopic quantum mechanics is going to play more and more of a role in our technology in the coming century. So what is macroscopic quantum mechanics? So if you have quantum mechanical particles, let's say bosons or fermions, usually you're dealing with them individually. But it's possible to put an infinite number of each type of particle into a single quantum mechanical state. And when you do that, you end up with an object which is big enough to see. It's big enough to hold in your hand. It's as big as a big superconducting magnet. The superconducting magnets in the LHC are 27 kilometers in perimeter, and they are a single large macroscopic object. So how does that work? Well, as a cartoon, imagine having particles in a box, bosons, let's say, and there's a lot of thermal energy, so the bosons are all jiggling around. But now you refrigerate them. You take away the randomness of the thermal energy, and their energy levels will start to fall. And eventually, because they're bosons, they'll all fall into a single macroscopic quantum state. That's called a superfluid. In the case of fermions, they can't all occupy the same state. So what they do in order to create a macroscopic quantum state, a superconductor or a superfluid, is that the fermions convert themselves into bosons first. Each fermion pairs with another fermion, and in doing so becomes a bosonic particle, and then they all condense into a macroscopic quantum state, a superconductor or a superfluid. So theory of Bose condensation was worked out by Bose and Einstein, and also Fritz London, very importantly. And Bose condensation, despite what you hear in the news media, Bose condensation was discovered by Kapitsa and Jack Allen in 1938. Fermions condense because they can form Cooper pairs. These objects are called Cooper pairs, and this theory is the Bardeen-Cooper-Schrieffer theory. Fermi condensation into superconductors was discovered by Karmeligonis in 1911. Okay, so here's the history of discovery and beginning to understand macroscopic quantum states. So Karmeligonis found 2 electrons form a 2e charged Cooper pair, superconducting state in 1911. Kapitsa and Allen found Bose condensation in superfluid helium-4 in 1938. My colleagues at Cornell, Richardson, Lee, and Osheroff, found Fermi condensation in superfluid helium-3. 2 helium-3 atoms condense into a Cooper pair. This has nothing to do with electrons. It's 2 fermions forming this new quantum mechanical state. They found that now 40 years ago in 1972. And then in the mid-90s, it became possible to form Bose condensation from tenuous vapors. That was first done by Eric Cornell and Carl Wyman. And then finally in the 2000s to form Cooper pair condensation from tenuous vapors. That was first done by Debbie Jeet. So here's a century of effort trying to find and understand these macroscopic quantum states. To me, this is extremely compelling and interesting area of physics. Okay, so let's turn to, and so when I started my career less than a decade after this discovery. So the hottest thing in town in those days was superfluid helium-3. So let me tell you a little bit about that. Superfluid helium-3 goes into its superfluid phase, a simple B phase, the one I worked on, at temperatures below 1 millikelvin. 10 to the minus 3 Kelvin, 10 to the minus 3 above absolute zero. And realistically, we have to do our experiments down here near 10 to the minus 4 Kelvin. And this state was discovered and understood by these gentlemen, all of whom received the Nobel Prize for it. And even today, superfluid helium-3 is the most well understood of all macroscopic quantum states. It's a very beautiful but complicated system. Anyway, we typically did our work down here near 100 microkelvin. So here you recognize this well-known New Yorker. And this is Richard Feynman. So in the late 50s, Richard Feynman made the following prediction. He said, suppose you have a macroscopic quantum state. It's got a single wave function into which all of the particles are going. Not one particle, but let's say 10 to the 30 particles. There it is. Now, it's got an amplitude and a phase. Now, think of that phase like a propagating wave. It's quantum mechanics, so if the particles are moving, it is a propagating wave. This phase is k dot r minus omega t. And forget the time dependence for the moment. Just focus on k dot r, okay? So the momentum of a particle in the fluid is h bar k. That's the de Broglie relationship, and it's definitely true in a superfluid. Now, k up here, if I relate this k to that phi, then I can write k dot r as gradient of phi dot r. So h bar k is h bar gradient phi. That's a mathematical statement. But the momentum of a particle is a real thing. It's the mass by its velocity. So now you get a velocity of the particles in the superfluid related to the gradient in the phase. And that's interesting because a classical property of a fluid is its circulation. It's the line integral of the velocity around a closed loop. There it is. But now if you take this velocity from here, substitute gradient of phase divided by m, the line integral of the gradient of a quantum mechanical phase around a closed loop is fixed modulo 2 pi. It can't be arbitrary. It's either 0 or 2 pi or so on. So the fluid circulation, according to Feynman, in a macroscopic quantum fluid is quantized in units of Planck's constant divided by the mass of the particles in the fluid. Now that's a weird idea. I mean, and what I want to tell you is that normally we get to forget these ideas and say, okay, that's some quantum mechanical thing which you will never observe. But you can make a bucket of superfluid this big. What this equation says is that if you stir the superfluid, either it will not swirl, or it'll swirl with 1 quantum, or 2 quanta, or 3 quanta. The fluid dynamics will be different than anything you have ever experienced of macroscopic physics during your life. So you could say, okay, Feynman is crazy, and there's no point in pursuing this crazy idea. But as you all know, Feynman was not crazy. And this actually is a very interesting idea. Now, to search for that idea, when I started at Berkeley, my advisor, Richard E. Packard, very famous low-temperature physicist, said to me, okay, here's Feynman, here's his equation. Why don't you just go and do an experiment to find out that macroscopic circulation is quantized in superfluid helium-3? Okay, so the first thing you got to do is cool the helium-3 down to about 100 microkelvin. And you're not cooling a few atoms, you're cooling kilograms of material to those temperatures. You do that by using a nuclear demagnetization cryostat. Here's liquid helium-4, superfluid helium-4. Here's the dilution refrigerator, the bottom of the dilution refrigerator, 10 millikelvin. Here's a big chunk of copper, which is magnetized, cooled to a few millikelvin, and then demagnetized, and it cools down to about 50 microkelvin down there. So first you got to do that. No problem. Well, it's actually it's a lot of problem. It takes years to do that. And there are very few labs left that can do this, even though there were many in the 1980s. But now, in addition to that, in order to look for the superfluid circulation, you have to stir the fluid. So how do you stir a fluid which is at a sub-millikelvin temperature? Well, the way you do it is you take the whole thing and rotate it steadily while it's warm, and then you cool it down to microkelvin temperatures, and then you stop, and then the apparatus will be stopped, but because the fluid was rotating when it went into the macroscopic quantum state, it'll still be rotating. So that's what Richard Packard told me to do, and you know, on paper, that's basically impossible. No rational person would do that. But I learned a lot from him about this method of analysis. The fact that it's perceived to be extremely challenging, if not impossible, is actually a highly beneficial indicator, provided it's a good theoretical prediction, that you should pursue that direction of research. So here's what we did. We built one of these nuclear demagnetization machines. And then up here, there's a vertical and radial air bearing, pressurized air, which lifts the whole thing up by a few thousandths of an inch on a cushion of air. And then all the vacuum systems for our refrigerator all pass through concentric rotating vacuum seals so that we could rotate this table and the container of helium-4 suspended from it up to 4 radians per second. 4 radians per second is just a little bit less than 1 cycle per second. This thing weighs about a ton, so when it was going at full speed, it was actually very impressive. Deep inside this apparatus is the chamber containing the liquid helium-3, and here's the experiment we carried out. So we wanted to find out that the circulation in a torus, let's say, is quantized in these units because the mass of the condensed helium-3 atoms, because they're fermions, is twice the mass of a single atom. So we took a cylinder with a fine superconducting wire down the center and a transverse magnetic field to the wire. Okay, and then we rotate the whole torus, including the fluid in this cylinder, while cooling from above the critical temperature into the superfluid state. So then when we got to a very low temperature, say 100 microkelvin, we halted the cryostat so that now the apparatus is not moving, but because it's a superfluid, the superfluid continued to move. And this is actually the most amazing thing. If you don't warm up and a superfluid is swirling, it just keeps swirling. You can come back 3 weeks later, it'll still be swirling. So the fluid is swirling now around this fine superconducting wire. So how do you measure the circulation? You drive a little pulse of current through the wire, okay? And there's a transverse magnetic field. So when you drive a current through the wire, there's a Lorentz force pulling the wire out of the board towards you. So it's like plucking a guitar string. So you pulse a current through the superconducting wire, and that plucks the string with the circulation around it. And now the string with the circulation around it is moving. So it's like a tornado with a wire down the center. It starts to move towards you like this. But when you move something with circulation through a fluid, it feels a transverse force, the Magnus force. There it is. So if you move something with a circulation around an object through a fluid, it feels a perpendicular force. That's how a baseball or a soccer ball curves. So while the wire is moving in this direction, it's feeling a transverse force. So it starts to move towards you, but it feels a transverse force. So the motion starts to precess. It keeps precessing, starts to move towards you again, it precesses. And this is the signal, the EMF detected at the ends of the wire due to the fact that this moving wire is in the presence of a transverse magnetic field. So when the wire is moving perpendicular to the field, you have a large EMF. When the wire is moving parallel to the field, you have zero EMF. And so from measuring the EMF as a function of time, you could tell at what rate that wire was precessing. And then from theory, you can measure the circulation on the wire. And in fact, during the experiment, we were able to change the circulation on the wire from one condition to a different condition. Sometimes we had a certain period, sometimes we had a different period. So at the end of the whole project, we were able to measure the circulation trapped on that fine wire. It was either 0 or 1 quantum or minus 1 quantum. Feynman was right. You can't swirl a superfluid except at quantized speeds. So this was the first project I worked on now 20 years ago, and I really learned and enjoyed a lot in doing that. And I used many of the guiding ideas that I learned in this project in subsequent projects. Okay, so next thing I wanted to do after joining the faculty at Berkeley, so here is Brian Josephson, very, very famous physicist for many different reasons. So Brian Josephson, while he was still a new graduate student in Cambridge in the late 50s and early 60s, understood superconductivity and predicted the properties of macroscopic quantum devices, most notably the Josephson junction, for which he got the Nobel Prize. Embedded in the end of his first paper, there's like a two-liner in the end of his first paper where he says, these properties of superconductivity, namely the Josephson junction, should also exist in superfluids. So in a superfluid, this is what he was implying. You have, let's say, a tube with superfluid in it, and it's in some macroscopic quantum state. All the particles are in the same quantum mechanical state. Okay, so now Josephson said that if you have two realms of the container, two volumes, and they're connected by a quantum mechanically weak connection, a weak link, then if you measure the phase difference, the quantum phase difference between these two volumes in the presence of a current traveling in the tube, two things happen. One is that the phase difference, h bar d phi dt, that's like h bar omega, is controlled by the pressure difference between each side, divided by the density, multiplied by the mass of the condensed particles. For those of you familiar with liquid physics, this is just the chemical potential per particle. This is actually Schrödinger's time-dependent equation. H bar, rate of change of quantum phase, is energy per particle. That's what Josephson had written down for the superfluid case. And then he could make that observable because he also showed that if this contact is weak enough, the current through this little Josephson junction would go as the sign of that same phase difference. And of course, this was all demonstrated very beautifully already by the early 1960s for superconductors. However, into the 1990s, it had never been detected for a superfluid. It was an outstanding challenge to do this for a superfluid. So here's what you really need to look for. So this thing symbolizes the Josephson junction. It's got some nanoscale engineering in it. It's a quantum mechanical link between two containers of macroscopic superfluid. Here's wave function 1, here's wave function 2. The phase difference between the two superfluids, phi 2 minus phi 1, I just call phi, as Josephson did. And so here's the first Josephson equation again. Rate of change of phase difference is the chemical potential divided by h bar. Then the other equation is the current equation, which says the current, the mass current, it's not a charge current, it's a mass current or a number current, through this loop is the sign of the phase difference. Here it is. Now for superconductors, the chemical potential per particle is of course the voltage. That's what the voltage is. But for a fluid, the chemical potential per particle is the pressure divided by the density multiplied by the mass of the particles. Okay. Now let's see what this thing predicts. d phi dt is something divided by h bar, which we assume is a constant. We can integrate this equation if the chemical potential difference is a constant, and you just get phi of t is chemical potential over h bar growing linearly in time. Simple. Now take this phase as a function of time and substitute it into the current phase relationship. You'll get current is some constant sine this number times t, sine omega t. Now this is where the counterintuitive nature of macroscopic quantum physics comes in. What this says is that if you have two containers of superfluid and you try to push liquid from one to the other through a Josephson junction, it will not travel. It's like squeezing a tube of toothpaste, but the toothpaste never comes out. Instead, what happens is the mass oscillates back and forth at this frequency, the Josephson frequency. And that's the equation for the Josephson frequency. This had been predicted since the late 50s, but never observed for a superfluid. Now, to do an experiment like that, you need two reservoirs. So we made a little little pillbox-shaped container about the size of a quarter with a flexible membrane on one side and embedded it in another box. So this is the first wave function in here. This is the second wave function out here. And the weak link, the Josephson junction, was a electron beam fabricated nano aperture. So you have a flexible membrane of area A, and it's got a spring constant. And you've got a fluid everywhere of density rho. Okay, so what can you measure in this apparatus? Well, if you can measure the displacement of the membrane from equilibrium, the pressure difference is linear in the displacement. It's like a balloon. When the pressure is higher on the inside, it displaces the membrane by a certain constant. Pressure difference is linear in displacement of the membrane. That's one thing you can measure. The other thing you can measure is the mass current. If the membrane is moving forward, it's pushing the fluid out from in front of it. And where does the fluid go? The only place it can go is exiting through this aperture. So the current through this aperture or junction is the density of the fluid by the area of the membrane multiplied by its velocity. Very, very simple ideas. But now let's look at how big Bryan-Josephson superfluid current would be. The density of liquid helium-3 is about 100 kilograms per cubic meter. It's actually the lowest density fluid of any fluid, but it's still pretty dense. And the critical current is known from theory to be about 1 kilogram per square meter per second. And order of magnitude area of this hole here is about 10 to the minus 14 square meters. So that means the current is predicted to be about 10 to the minus 14 kilograms per second, the Josephson current through that hole. Okay, so how big would the displacement of the membrane be? Well, the current is density times area times velocity of the membrane. The area of the membrane is about 10 to the minus 4 meters. The density is about 100. So that means the velocity of the membrane would be about 1 picometer per second. That's pretty small, but not crazily small. Unfortunately, though, there's no DC flow. It's the AC Josephson effect. The thing is only going to oscillate back and forth. So suppose it's oscillating at a few hundred hertz in the audio range. Let's say omega is 1,000 radians per second, okay? Then the velocity is omega times the amplitude, or the amplitude is the velocity divided by omega. Amplitude of motion expected here was around 1 femtometer. So the reason why that this was known to be impossible is that no rational person would attempt to make a flow experiment where the displacement of the measurement membrane is of order a femtometer, 1/10 of the diameter of one nucleus in the apparatus. Okay, so however, as I'm trying to tell you with this lecture, this actually was a very important clue that it was the correct experiment to pursue. It's not that it's impossible, it's that the people who had considered it didn't think sufficiently clearly about how you would measure displacements of order a femtometer. How would you do it? Well, gravity wave antennas do it all the time. they measure displacements down to around 10 to the minus 18 meters. Here's an aluminum gravity wave. It's the Auriga gravity wave antenna in Italy. And over here, there's a squid-based position sensor, which can measure the displacement of the end of this aluminum bar to about 1 part to about 10 to the minus 18 meters. So, faced with the challenge of measuring the motion of our membrane in the femtometer range, and knowing that this technology exists, then you do the obvious thing. That's another piece of advice that I can give anyone. Do the obvious thing, which is that take the gravity wave antenna sensor and embed it in your apparatus so that you can measure the location of this membrane within a few femtometers. And that's exactly what we did. We used a superconducting position sensor here in front of the membrane. This is a diagram of the real apparatus. We were getting about 10 to the minus 15 meters per root hertz and a 50 kilohertz bandwidth. And actually, to make our signal a little bit bigger, instead of 1 aperture, we actually took several thousand apertures to increase the signal to noise. And finally, if you make an apparatus which has an acoustic membrane in it, which can hear displacements of order 10 to the minus 15 meters, okay? That's a microphone which is about 10 to the 12 times more sensitive than the microphone I'm using here, or a typical microphone. And it's about, well, let me put it this way. If you make a microphone like this, you can hear everything that's going on in the building. You can hear people talking down the corridor. You can hear toilets flushing. You can hear the elevator going up and down. You can hear people parking outside. You can hear everything. They're very strange devices. But the problem is, when you can hear everything, all of that everything overwhelms your experiment. So the other thing you have to do when you make an ultra-sensitive experiment is to shield it from the outside environment. So we had to develop, this is Ray Simmons, who was my graduate student then. He's now a group leader at NIST. We had to build this underground, acoustically isolated, ultra-low vibration lab within which the ambient amplitude of acoustic noise is in the 10 to the minus 15 meter range. It took us a while to figure out how to do that. And of course, we needed this millikelvin cryostat to cool the superfluid to the correct temperature. Anyway, at the end of the day, here's my equation of motion for the membrane. d phi dt is supposed to be related to the pressure difference between the inside and the outside. The pressure difference is related to the displacement. So if I take d2 phi dt squared, it's related to dx dt. But dx dt is the current. So I can substitute here the mass current. I get d2 phi dt squared is linear in the current with some constants. And finally, if Josephson was right, the current would go as the sine of the phase. So d2 phi dt squared equals some constant times the sine of the phase. Phi double dot plus omega squared sine phi equals 0. Those of you who remember your classical mechanics will remember that that's the equation of motion of a physical pendulum. Physical pendulum in the sense that at some high amplitude of motion, the pendulum can go around quickly. And then at a lower amplitude, it has nonlinear oscillations. And then at the lowest amplitude, it has linear oscillations. So that's predicted. The dynamics should be identical to those of the velocity, angular velocity of a physical pendulum. Those are the 3 cases I just described to you. You should see all of these 3 cases in the motion of the membrane if Josephson's theory of the superfluid Josephson effect is correct. So, okay, we do an experiment where we apply electrostatically a pressure difference between this sample of superfluid and this one, and we monitor the time dependence of the position of this membrane with femtometer sensitivity. We should expect to see high-frequency Josephson for finite pressure differences. We should expect to see high-frequency Josephson oscillations, this thing. Eventually, though, when the pressure falls, we should expect to see a transition to highly nonlinear Josephson oscillations, this thing. And then when the pressure falls to the minimum, we should expect to see linear harmonic oscillations. That's the combination of all the predictions from this equation of motion for a superfluid Josephson junction. I wouldn't have told you all that if the experiment didn't work. In fact, what you see is high-frequency Josephson oscillations here. I'll show you them in a second. and then the transition to low-frequency nonlinear dynamics, and then eventually those become linear oscillations. Here, you can't actually see the high-frequency Josephson oscillations in the signal, and in fact, we didn't see them for many months. We kept doing this experiment over and over and over again. We couldn't find the thing we were looking for, until finally my postdoc, Sergei Perverzev, took this signal, which is a voltage coming from the squid, and he put it into an audio amplifier, the one you use for listening to music, took the output of the audio amplifier, put it on the earphones, put the earphones on his ear, and then listened to this signal here, and what he could hear is, exactly as predicted. So there's a frequency linear in pressure, which there should be, and it's the relationship, the Josephson relationship is frequency is this number of kilohertz per Pascal, and at the end of the day, we were able to discover that that's actually true, more or less independent of any other condition. And it has to be true, because it's quantum mechanics. There's no degree of freedom in the equations. So this was the discovery of the superfluid Josephson effect. Gosh, how long is that? Almost 40 years after it was predicted. Okay. Now, I'm going to change gears. I moved on from there. I started working on the high TC superconductivity problem, but carrying along the baggage of all the stuff that I had learned, and also moved over to Cornell University. That previous work was done at Berkeley, but moved over to Cornell and also Brookhaven National Lab. And this collaboration has been a ball of fun for us. What we turned over to is a different problem. How do you visualize macroscopic quantum phenomena, especially for electrons? Normally, you don't think you have to visualize electrons to figure out what they're doing, but there are a few important cases in which you do need to visualize what they're doing. So we started a program to try and visualize electronic quantum matter. The reason we did it is there's a race to find room temperature superconductivity. Now, for those of you unfamiliar with superconductivity, in terms of technology, the key thing is that it allows lossless electrical and electronic technology. You could generate and transport electricity with no losses, and you could transport it across the continent perfectly efficiently with superconducting power lines. Or, for example, if you had a superconducting iPhone, the battery would never run out because the operations would be dissipationless. Of course, it would run out because of the screen, but in terms of the data processing, it would be a dissipationless device. Or, for example, your laptop would never get warm because during the calculations, no heat would be generated in a superconducting laptop. So here's the critical temperature at which materials go superconducting into this lossless state. And this is in Kelvin, so minus 270 degrees Kelvin for many decades. But now in the last 20 years, it has started to shoot up. There's two families, copper-based and iron-based superconductors, and they both look like they have the possibility of heading towards room temperature. If we could do that, there's all kinds of wonderful things we could achieve. Lossless power transmission. We could rewire the cities with lossless power cables. We could accommodate renewables. There are high-energy physics reasons why we need high-temperature superconductivity, medical reasons, transport reasons. And right here in the middle, something most people don't realize is our most rapid rate of use of energy in our civilization is server farms. We're using an enormous amount of energy for Google to answer your query before you finish typing. Requires a huge amount of energy. So we could replace these highly energy inefficient systems with superconducting server farms. That would be fantastic. Okay, so how do you get to room temperature superconductivity? The people involved in this business believe that there's some relationship between antiferromagnetism, that's a magnetic state where every spin is anti-aligned, up, down, and the appearance of high temperature superconductivity. There are many systems where when you destroy the antiferromagnetism, the superconductivity appears. Here's the copper-based high TC superconductors. You destroy the antiferromagnetism, the superconductivity appears. Here's the new iron-based. You destroy the antiferromagnetism, the superconductivity appears. At the level of hand-waving, everyone is pursuing this idea. But there are problems with pursuing it, and here's a key one. in almost all these systems, you start with a poorly conducting or even insulating antiferromagnet. You put some dopant atoms into the crystal, the antiferromagnetism disappears, and indeed, eventually, the superconductivity does appear. But we haven't been able to find the link between this state and that state, because in virtually all of these compounds, some other exotic electronic phase occurs in between. And those phases have prevented us from understanding the problem and have also basically deflected people's attention because they are very exotic and interesting. So in fact, we'd like to understand what these guys are. And I'd like to give you a motivation for what they might be. Imagine you have a simple vapor. Here's water vapor. It's isotropic, it's translationally invariant, and it's rotationally invariant, the properties of water vapor. Now, if you increase the interactions just between the water molecules, you get something which is far more complicated. You all know liquid water is much more complicated in its physics and its dynamics than water vapor. And if you increase the interactions some more, but before you get to ice, there are many liquids in which you get a liquid crystal state. So you go from an isotropic state to a strongly interacting state to a state which breaks some symmetry at the microscopic level, a liquid crystal state, which is not yet a solid. And of course, liquid crystal state, the classic liquid crystals, we're so used to them now, many of you don't even remember, or well, not even alive, when they were not available in our technology. But they've been miraculously important, the ability to understand and control liquid crystal states. There's two classic types of liquid crystal. One breaks rotational symmetry. Think of these as the molecules. It breaks rotational symmetry, but that's all. It doesn't have any periodicity in space. That's called a nematic. The other one breaks rotational symmetry and translational symmetry with a certain wave vector. That's called a smectic. Here's Pierre-Gilles Digende. So he figured this out in a theoretical sense in the early 1970s. He received the Nobel Prize for it. And the way he figured it out is by visualization. To understand how classic liquid crystal works, we had to wait until the 70s when phase contrast microscopy would allow us to see the relative orientation of the molecules in the liquid crystal down to the submicron scale. So visualization and understanding were closely related in the understanding of classic liquid crystals. Okay, now turn the page and think of a new idea. Imagine you have a isotropic, rotationally symmetric, featureless gas of electrons, the electron gas, in a piece of copper. You're all, at least intuitively, familiar with that. It has no real properties except that it's an isotropic fluid and it flows around the place. If you increase the interactions, you get a heavy electron fluid, which if I get time, I'll talk about, but I may not get enough time. If you increase the interactions some more, you might get a Wigner crystal. But starting in the 90s, a lot of theorists began to propose that in between, there could be electronic liquid crystal states. And that those electronic liquid crystal states are the mysterious states which are found between the antiferromagnet and the superconductor in the high TC superconductors. So both of those predictions actually were made in this famous paper by Steve Kivelson, Eduardo Fradkin, and Vic Emery, who worked here at Brookhaven a lot. So electronic liquid crystal. But what would an electronic liquid crystal look like? You need atomic scale visualization of complex electronic matter to find out what an electronic liquid crystal looks like. And it was widely believed that that's impossible, or at least so difficult that one shouldn't pursue it. There are two classic papers actually proving that you can't do this. In any case, we didn't believe that. We decided to look at the challenge of visualizing atomic scale complex electronic matter. How would you do it? Well, first you start with a scanning tunneling microscope. Very nice machine, already invented in the early 80s. If you scan a sharp metallic tip over a surface, you measure the tunnel current from the tip to the surface. If you feedback on that tunnel current, you can get an image of where the atoms are in the surface. So those atoms are, those are selenium atoms, as you can tell by looking at them. Okay, but the thing about scanning, and you can image, so these are bismuth atoms, these are calcium atoms, these are strontium atoms, these are uranium atoms. You can image atoms very, very nicely. It's a ball of fun. However, this machine does not allow you to image the electronic wave functions. It doesn't allow you to see the matter waves. You have to go beyond this technology. So to do that, we developed the idea of a spectroscopic imaging STM. What it does is it scans over the surface, but at each atom, it stops. And at that location, it measures the differential tunneling current as a function of the bias voltage between the tip and the sample. So some curve like this for that atom. So you go to this atom over here, you measure that curve, differential conductance as a function of sample bias. And in theory, this differential conductance is related to the density of electronic states at each of these energies. So you measure that at the first atom, and then at the second atom, at the third atom, and at the fourth atom, and so on. Measure this spectrum at every atom in this field of view. There's about 30,000 atoms in this field of view. So you take that spectrum at every atom. And at the end of the day, you have the value of this function, okay, resolved by energy. So in this field of view, if I look at this energy plus 50 millivolts, then the differential conductance is showed here by this bright dark scale. And then you have that image, you have that information at every energy, like this. You can think of this as a movie showing the wave functions of the electrons in the material resolved by location and resolved by energy. Energy resolved movie of psi squared of those quantum mechanical electrons. One way to know how that this was startlingly new and different in 1999 is that it was virtually impossible to publish the first paper because the referees just could not believe, A, that that nature is like this, and B, that you could actually do this experiment. And it took us several years to get the first paper out the door. But eventually we succeeded. And now this is a widely used technique. You're imaging a psi squared of electronic wave functions resolved by space and by energy. Extremely powerful technique. It's technically challenging, however. In fact, it was believed to be impossible. And the reason is, if you do the calculation for how carefully you have to stabilize the distance between the tip and the surface in order to get this complete data set. And don't forget, this is a big data set now. Suppose you take 512 by 512. That's 250,000 points. And then at each point, you take a couple of hundred data points in each spectrum. So that's 50 million data points. Okay, so in this movie, there's 50 million independent measurements. If you make 50 million of any measurement in 24 hours, you have only about 2 milliseconds per measurement. So it's very hard to do, and in order to get enough signal to noise, you have to constrain the tip motion, the RMS motion of vibration and thermal agitation of this last atom to about 1 femtometer. So the way we do that is we use an ultra-low vibration laboratory. We use an underground reinforced concrete vault with an anechoic chamber. And inside that, we have an acoustic isolation chamber on a separate floor, which has its own vibration isolator. And then inside this region, we have another isolation table. And then finally, we have the low temperature tunneling microscope. So here we have vibrations on the micron scale, nanometer scale, angstrom scale, picometer scale, and down inside the apparatus on the femtometer scale. We've just completed building a new one of these facilities here at Brookhaven, a tandem, 2 labs side by side. And they're really, really beautiful. We're going to move the first machines in here in a couple of months. OK. So let me come back to my objective, which is to find out what is this weird intervening phase here between the antiferromagnet and the high-temperature superconductor. So let's just jump to the experiments. Here's a high-temperature superconductor, and each dot here is a bismuth atom. And this is a cuprate superconductor, so for any experts in the audience, the copper atom is underneath each bismuth atom. So in this field of view, we image the wave functions of the electrons. Here's a movie. Now look carefully. You'll see the wave functions are breaking rotational and translational symmetries at some energies. And then at other energies, they're amorphous. They're de Broglie waves. They just have some interference. But here, you see they're periodic, and they're breaking rotational and translational symmetry. We made some careful double checks that this is a universal property of these high TC cuprate compounds. They all, at the correct carrier density, they all show periodic structures which are aligned in one direction. They obviously break rotational symmetry, and they also break translational symmetry. What you're seeing here is a picture of the electrons in a conductor spontaneously forming themselves into an electronic liquid crystal. And these were the first pictures of that type. So now quite a wide variety of researchers have been able to pursue this research agenda, but these things really were the first light pictures of electronic liquid crystals in these exotic materials. One thing we were suspicious of when we were looking at this data, you see that it has much finer detail in it. It isn't just these parallel stripes. Inside each stripe, there's much finer detail. We can look inside each stripe, zoom in a little bit more. Now that's 4 unit cells. It's about 16 angstroms. So this is where the atoms are. So this is copper, oxygen, copper, oxygen, copper, oxygen. So there's oxygen, 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 4 unit cells wide. One thing you notice immediately, look at that copper atom. So the oxygens on each side here are different than the oxygens on each side here. This oxygen and this oxygen are in a different electronic state than this oxygen and that oxygen. Nevertheless, according to the symmetry of the crystal, they should have been the same. There's no reason why the oxygen atom on one axis, on this axis, should have a different property than the oxygen atom on the other axis. And this led us to conclude that there's another broken symmetry, and it's inside the unit cell. And indeed, if you look inside each unit cell, you find out that there is a broken symmetry. It's intra-unit cell electronic nematic phase. And we were able to tease it out and quantify it by using the Bragg peaks of Fourier transform STM, which turned out to be a very nice step forward. So anyway, the 2 Bragg peaks are different. That tells us that inside each unit cell, the electronic structure along one axis is different along the other axis. And this is an electronic nematic. It's the second type of electronic crystal, which was expected by the theorists. Okay. So inside these intertwined mysterious phases between the antiferromagnet and the superconductor, now we are becoming rather confident that those intertwined phases are electronic liquid crystal phases. And the challenge really is, A, if you love them, to understand them, and B, if you want high TC superconductivity, to get rid of them, because they're the thing which is taking over the properties of the free electrons and preventing them from superconducting instead of at 150 Kelvin, at 300 Kelvin, which would be room temperature. So love them or hate them, these electronic liquid crystal states are very important for solving this problem. I didn't have time to talk about it, but we were also able to find an electronic nematic in the other family of high temperature superconductors, namely the new iron superconductors. I know I'm going to run out of time, so in order not to torture you, I shall just jump to the end of this presentation and say that, okay. In terms of the problems of superconductivity, we have been able to determine a great deal about the superconducting electronic states and the mechanism of those states, and also, and perhaps more importantly, by visualizing the electronic structure, determine what this intertwined or competing phase is like in these materials. Now, the last thing I wanted to say is, since this is my primary purpose here, I guess, is to say something about how to choose what research problem is of interest to you and what you should pursue. So based on my own experience, I tried to distill out what I would say, and here's what I would say. You want to choose a consequential problem, something which, when you solve it, it alters the economy, it alters our knowledge of nature, it does something relevant. If you don't see that the problem ever will have any consequence, then you really should ask yourself whether it's the right way to go. Second thing is, because we all live in a kind of a business environment, we have to sell our product as well as generating it. A very good idea is to choose a problem which is compelling. You know, if you're sitting on the subway and a person asks you, what do you do? And you tell them what you do, okay? If it's compelling, their eyes will open and they'll say, wow, that's really interesting. I wish I knew more about that. And if it's not compelling, they just fall asleep. Then you know you're on the wrong problem. The other thing is it should be clear. And this is something that it takes a while, I think, for people to learn. It took me a long time to learn. Real scientific success, even though it may be very complicated as you're going through the process, a real breakthrough when you come to the end game is not complicated. It's simple, it's straightforward, and it's clear. So you should be looking for things which are consequential, compelling, and clear. Also, and equivalently, they should be important. Should be important to you, they should be important to your colleagues, they should be important to your country and to the world. They should be impressive. This is just another way of saying this. When you're done with the job, if you tell people what you've done, they should be impressed by it. And finally, here's what the theme of my talk was about. They should, oftentimes, a way to choose a really good problem. If you already know that it's important and consequential and compelling, but your competitors believe it's impossible. And of course, it shouldn't really be impossible. If it violates Newton's laws, Maxwell's equation, or the Schrödinger equation, or the laws of thermodynamics, do not pursue it. Okay? But if it's merely perceived to be impossible because people haven't figured out how to do it right, they were not sufficiently disciplined to realize that it's perfectly possible if you find the correct solution, if you put in enough effort, then my advice is to pursue these things which are important, impressive, and appear to be impossible. Thanks very much.
Thank you very much. I think we have time for one quick question. The microphones are on the sides.
Yeah. Yeah, okay. That's a brilliant question. I don't think I can give the answer in public. No, okay. So in many of these projects, the motivation, so there were several parallel things going on at the same time. On the one hand, there's a relatively straightforward objective that you can put in your proposal and tell the funding agency, I'm going to find the pairing mechanism of high TC. Okay? They understand that, and they give you the money to do it. On the other hand, you have your own compelling agenda, which is associated with perhaps your deeper knowledge of the problem you're working on. And you have to be clever enough, on the one hand, to satisfy this direct and immediate and saleable objective, and on the other hand, to pursue the deeply fundamental things that you're going to work on. And I think most people who manage to get very challenging projects funded do it that way. They have a saleable thing, which is clear, simple, and the funding agency likes it. And on the other hand, they have another part of their agenda, which is related to the deepest intellectual problems in the same area. If you're clever enough, you can combine those together.
Let's thank Professor Davis one more time.